speaker. I do see that Jenne Driggers has been able to join us, and she's got her slides shared, which is great. Jenne is a staff scientist with LIGO Laboratory. She's works at the LIGO Hanford Observatory in Washington State, America. Hi, Jenne. Nice to see you. Good morning.
Hello. I hope you can hear me okay.
Yes, you are clear, and you're welcome to start whenever you're ready.
Thank you for inviting me to come share some of what I do and my love for the gravitational wave interferometers with all of you. Martine just shared with us how you can access and utilize the open data from the gravitational wave interferometers around the world. I will share with you a little bit about where did that data come from and how do we create that data? How do we know what kinds of signals may be in that data in terms of amplitude and phase, and what do we know about that data? So first of all, there are many interferometers around the world, and I hope that this is not new information, but it's very exciting that we have several world-class gravitational wave interferometers around the world. I work at the LIGO Hanford Observatory here in Washington State in America, in the United States of America. We have a second interferometer that we operate in Louisiana in the United States of America, and these two detectors are very similar to each other in terms of technology. We also work closely with the Virgo interferometer just outside of Pisa in Italy, as well as closely with colleagues from the Kagra interferometer in Japan, which here you can notice that this is, rather than a true photo, this is rendering because the Kagra interferometer is underground to help isolate from seismic motion. So they've implemented their technology underground to get advantages from being away from the Earth's surface. And we're also very excited that in the coming years, we will have yet another ground-based interferometer, LIGO India, and they should be coming online, hopefully in the next some number of years. After that, there are other future detectors which are in planning stages and proposal stages, but these are the interferometers that are kilometer scale baseline for these arms that are currently operating or very, very soon to be operating. I say kilometer scale because these are small photos, and for that I apologize, but this is a building. You can't even see the cars parked at the building, and the arm length is 4 kilometers into the distance from the main building. So these are really truly large scale detectors to provide the data that Martine was just telling us about. So I'll talk a little bit about how do we use these machines to measure gravitational waves from astrophysical events, and touch very briefly on how do we calibrate them so that we know what amplitude, what signals we are seeing should we see a signal. So first of all, very, very briefly, gravitational waves are ripples in space-time. They're affecting space-time itself. So in the upper corner, I have this simulation of 2 black holes inspiraling around each other, and they are about to merge into a single final black hole. As they spiral around each other, space-time, they're emitting gravitational waves, and space-time is stretching and squishing as the gravitational wave travels along this blue tube. And LIGO and our colleague interferometers measure these distortions of space-time itself. So if we think about in just a different plane, a different dimension, we have our blue tube of space-time that will stretch and shrink as a gravitational wave passes through the plane of the screen. we can think to put a laser and a beam splitter in the center of, not necessarily in the center of, but somewhere in space-time. And then as the gravitational wave passes through the plane of the screen and space-time stretches and squishes along these axes, this will move these mirrors because these mirrors exist within space-time. And using this laser that we can send and split the beam in half, 50% will go one way and 50% will go the other way. And then as these mirrors move, it will create an interference pattern here at the beam splitter. The light will recombine and go towards a photodiode. And on this photodiode, we will measure how much light is here. And that tells us about the interference pattern, which holds information about how space-time is changing, how space-time is moving. So here I've got a video showing that again. Here's a laser, a beam splitter, and the light goes to the end stations, the end mirrors. And then if a gravitational wave passes through this little interferometer, the mirrors move. So here we've got the light, and the light is represented as a sine wave. It reflects off of the end mirror and also the other end mirror. And as the light is recombined at that beam splitter, it happens that here there's no light. They've interfered deconstructively. But as the end mirrors move, it changes the interference pattern of these two sine waves, and we see more or less light on that photodetector. So this is how the photodetector signal can tell us about how much light is here, and which then tells us about how these mirrors were moving. And since those mirrors exist in space-time, how space-time was changing with time. So that was a very basic Michelson type interferometer. And that is indeed what our gravitational wave detectors are based upon. However, we have many, many extra components which we use to allow for much more sensitive detection of the gravitational wave signals. So here in this cartoon, I've got my main laser. We've got several subsystems to stabilize that laser in frequency and intensity, because the laser is the ruler with which we are measuring how much the mirrors are moving. So the laser needs to be very, very stable. And so we use several subsystems to stabilize that laser. We then send the laser light into the main interferometer, and we have that same beam splitter that provides that same function to split the light, half going to one arm cavity, half going to the other. And then the light is allowed to recombine, come towards the output of the detector. The light is cleaned up a little bit more with yet another subsystem. And we finally go to the actual gravitational wave detection photodiode detection port. All of these other mirrors, in addition to allowing for some steering that is kind of indicated here, allow for us to increase the amount of laser power that is contained in the interferometers. So these represent our 4-kilometer arm cavities, and we can use them to build up the laser light more and more and more. And this improves our sensitivity at higher frequencies by having more and more laser light that is present to measure the motion of these mirrors. Due to conservation of energy, any light that did not, when we have our interference at the beam splitter, if we have deconstructive interference here going towards our gravitational wave port, that must mean that we have constructive interference and lots of laser power traveling back towards the main laser. And one way that we can think about this is light that did not detect a gravitational wave signal. And so we put in a recycling mirror to turn that light around and have it go back into the main interferometer and try again to measure gravitational waves. So this, in effect, allows us to build up our laser power even further, because the main laser, while we do have phenomenally exquisite lasers, there is a limit to how powerful of a laser can be made at the stability that we need. And so we utilize these other techniques to build up the laser power in the interferometer to improve our sensitivity at high frequency. The other big extra component here is a signal extraction mirror. And this mirror is used really to adjust the frequency dependence of our ability to detect the gravitational waves. This allows us to detect gravitational waves over a more broad frequency so that we'll be able to see more components of the astrophysical signal. And you'll hear more about the astrophysical signals themselves later. But this allows us to tune what frequencies we are sensitive to. I like to show this photo. This is our instrument hall at the LIGO Hanford Observatory. Just to give you a scale of, those were cartoons. This is the real detector, and this is the detector that I work at. And so this is the actual hardware that we utilize to detect gravitational waves and send the data out to places like the Open Science Center. And here I overlay a cartoon of our main laser is in this corner of the room. We've got our main beam splitter not so far from the laser. The beam splitter indeed splits the light about half and half, going through to these arm cavities. And it's difficult to see in this photo, but the laser beam is traveling through the vacuum tube and out into, continues out in the vacuum tube, out for 4 kilometers before it hits the end mirror, reflects back, and comes towards the main hall again, hits the beam splitter to recombine, and then finally we'll go to the gravitational wave photodetector here in this corner of the room. So why do we do all of this, and why do we work so hard to put all of this hardware together to detect the gravitational waves? It's not trivial. It's really very, very difficult to measure something at this small of a level. So this plot I show, there's no data here yet, just so that we can talk for a moment about what it will show. On my x-axis, I have frequency. So I know that there's been some chat in the chat window during Martine's presentation about what kinds of FFTs and stuff we can use. So that's one thing we do when we're looking at the noise performance of our interferometer. We do an FFT to using the Welch's method to look and see what amplitude of data we have at each frequency. So we usually look between about 10 hertz and a few kilohertz. And the signal that I'm interested in usually is how much are our mirrors moving? How many meters are we sensitive to? How many meters of motion are we sensitive to? And these are 10 to the minus 15, 16, all the way down to 10 to the minus 20. And just for some sense of scale, the diameter of a proton is about here at the top of the plot. So we're measuring things that are much more sensitive, much smaller size scale than the diameter of a proton by orders of magnitude, factors of 10. So this is an image of some of our data from, this happens to be 2019 data during our 3rd observing run. And it shows many different traces, but in particular, the purple line is the design sensitivity of the gravitational wave detector. So how sensitive we think that our hardware can enable us to detect gravitational waves. And these other traces in red, yellow, and blue are the sensitivity of the actual gravitational wave detectors at some point in time. The blue is the Louisiana detector, and the red and yellow are two different points in time of the Hanford interferometer. And you can see that particularly above 100 hertz, we are impressively close to where our design sensitivity is. So we do a nice job of achieving the sensitivity that we think that the hardware can give us. And so this says that this is kind of our baseline noise level. So should a gravitational wave come through our detector, as long as the effect it has on the mirrors is larger than this many meters of motion at each given frequency that the gravitational wave signal is at as it moves through time, we should be able to detect that gravitational wave as long as it's larger than our baseline noise. And how high above the baseline noise the signal is can give us information about how well we are able to measure that signal. And obviously we would like to improve and lower our baseline noise sensitivity so that we can continue to measure gravitational waves with higher and higher fidelity. This is just another way of thinking about, just to really clarify, because it's such an impressively small number that we're measuring for the distance of the meters. And because what really matters is not the individual motion of a mirror, but the motion of the mirror divided by the beamline that it is looking at. So for LIGO, it's 4,000 meters, 4 kilometers. So our mirrors move on the order 10 to the minus 19 meters, and that is divided by 4,000 meters, because that's the gravitational wave strain that matters for measuring the gravitational wave signal. How much the mirrors move divided by the total baseline. And that's equivalent to measuring, again, this is a ratio, the width of a human hair, level of precision, the distance between the sun and the next star. So that's how very, very precise the gravitational wave interferometers are. There are many reasons why we are and are not able to measure more sensitively at different frequencies. And this is a plot showing some of the contributions to the sensitivity. This is a really complicated plot, so I'll just touch over it a little bit briefly. In red on this trace, we have the actual measured sensitivity of one of the gravitational wave interferometers. And in dashed line, we have what we think that we should be able to achieve once we are completely done with our next several years of installation of hardware and software and other technologies. Importantly, this includes much higher laser powers than we have had in the past. The rest of these traces show the limits to why is this red trace not better. And so one of the big limitations in this light blue trace is the quantum noise due to the quantum shot noise. And that's related to the amount of laser power that we have available to be measuring the gravitational waves and to be illuminating those photodiodes to show that we can actually measure the voltage of that photodiode. So you can see that with our current laser powers, we are limited at this level. And so that's why we're not measuring better. So we know that should we be able to improve our quantum shot noise here at high frequencies, we can allow ourselves to measure more sensitively at these frequencies. At lower frequencies, there's a different quantum effect, which is quantum radiation pressure, that we'll talk about in a little bit in more detail. And that is a limit to what we expect that we are able to do eventually. The design sensitivity, it's a limit to the design sensitivity in the dashed curve, but that's not actually the most important noise source that contaminates our gravitational wave signal. Our most important noise source right now is controls noise, which is shown in this dark purple curve. So, and that is because in order to actually keep all of this laser power circulating in the interferometer, we need to keep our laser beam pointed so that it matches the alignment of the mirrors and that the mirrors are well aligned to each other and that laser beam. We also require, in order to build up interference inside the interferometer to build up the laser power higher and higher, that mirrors are held at an integer number of half wavelengths apart. So we have to hold our mirrors a precise distance apart as well as a precise alignment. And to do that, we need to push on the mirrors to hold them still where we want them to be. And that all adds up to contribute to this controls noise. And so we hope that as we improve our controls loops and other technologies, we can lower this noise and bring it closer to the design sensitivity. And that will enable us to have better measurements of gravitational waves at these lower frequencies. So I've told you about the sensitivity of our gravitational wave detectors, but how do we really know how much our mirrors are moving? We have to know somehow at some precise level in order to be assured that we're sharing data, that we're confident what the data means. And the main way that we calibrate our interferometer and the motion of the mirrors is with photons themselves. So we have an auxiliary laser, an extra laser. This is a cartoon of the end mirror. So this interferometer beam comes from off the screen, the main beam splitter, and it has traveled 4 kilometers to our end mirror. And a few meters away from the end mirror, we shine an extra laser at the mirror. And because the laser light carries momentum, this laser beam, as we shine light onto the mirror, it imparts momentum and causes the mirror to move. And the force that is applied to this mirror is related to the power of our extra laser divided by the speed of light. And there's a factor of 2 because we've reflected off of the mirror. So in order to do this reflection, to get the light to reflect off, to change directions, we had to impart momentum onto the mirror itself. And so equal and opposite reactions, if this laser light bounced off of the mirror had to react and move. And this is related to our radiation pressure. This is a type of radiation pressure. But here we have a very, very extremely well calibrated laser from our National Metrology Institute here in the United States is NIST. So they have told us with very exquisite precision how powerful is this laser and what is the amplitude of this laser light. So we know very, very precisely how many photons we are hitting our mirror with. So we know very precisely what force we are applying to our mirror. And since we then know how our mirrors respond to the forces, then we can know how much the mirror must have moved due to this light from the extra laser beam. Something that I've glossed over, but I'll come back to now very briefly, is that our mirrors, because we want them to exist and kind of float in space-time, but we are a ground-based machine and so have to live in a world of gravity. What we've chosen to do is we suspend our mirrors as a pendulum. And so we know how that pendulum responds to the forces applied, such as this extra laser beam. And so since we know what our pendulum will do as a function of frequency when force is applied, then we can know how much did the test mass, which is what we call our mirrors, it's a test mass existing in space-time, how much did it move due to this auxiliary laser? And then we can make sure that the data we send out from, because then this motion of the mirror affects the main interferometer beam and will show up in the data at our gravitational wave detection port. And we make sure that the data that comes out our gravitational wave detection port matches very well the motion, the meters of motion that we have imprinted, that we have put onto the laser beam by having moved this mirror. We don't care so much just at DC at low frequency, like extremely low frequency, like 0 hertz, just by pushing. We don't care so much about the calibration at that low of a frequency because we are on the ground and we have seismic motion and we can't detect gravitational waves with excellent ability at infinitely low frequency. But what we do care about is the data and the calibration of the data above a few hertz and up to a kilohertz and beyond. So what we can do is we can modulate the power of this auxiliary laser. So we can have it be more laser power, less laser power, more laser power, less laser power. And we can do that at a frequency that we choose. And then that moves this mirror at that frequency by a known amount. And so we can compare as a function of frequency, our calibration of this, of what we know the mirror is moving to the data stream. So something to note is that we always have calibration lines present in our observational data to monitor as a function of time the accuracy of our calibration and to monitor should anything change about the whole interferometer, we can know that nearly instantaneously and we can correct for that. During maintenance periods of the order once per week, we take a much more detailed calibration measurement at many more frequencies to be assured that our full calibration is as accurate as possible. When we calibrate, of course, we say that we know very, very well what the amplitude and frequency of our mirror motion is, the data to mirror motion. But there is, of course, a limit to how well we can know. And the systematic error reports how well do we know our calibration and how well can we truly say we know our mirrors are moving based on our data. So these plots are as a function of frequency, starting at 10 hertz, going up to 5 kilohertz. This is the amplitude of the signal, and it is a ratio of a measured, using those laser calibrators, measured response of the mirror motion to an expectation of what our current or previous calibration was. And then we divide by 1 so that this is a percent error from what we thought we had. So we measure it sometime and compare to what we thought we had. And within a 68% credible level, for the most part, particularly where the gravitational wave merger happens and some of the ring down, we are much better than 2.5% error. So we can say that we know our calibration to better than 2.5%. And similarly, we also care about the phase of the data, because the phase of the data also can help tell information about the object that created the gravitational wave signal. And so this is, as a function of phase, what is the difference between our measurement and our calibrated, like what we thought the calibration was. And again, you can see that it's very, very exquisitely small, that we know very, very well how well we understand our calibration. These calibration uncertainties are folded in when we do analysis of our data to try and understand the astrophysical parameters of objects that created a gravitational wave source. For example, the masses of the black holes or neutron stars or whatever other object, how far away that gravitational wave source is, other parameters. Our uncertainty in being able to say what those parameters are, part of that comes from this calibration uncertainty of how well are we able to calibrate the data that comes out of the interferometer itself. As a final thought, I'll share with you our kind of history of improvements in that sensitivity as a function of time and where we think that we can go in the future. So I hope you know that we've had 3 very successful observing runs so far, which we call observing run 1, observing run 2, and observing run 3, 01, 02, and 03. And the gray, yellow, and red traces are measured data, measured sensitivity from those 3 observing runs. And you can see that we've kind of slowly made progress between our first and second observing runs. Our third observing run, we were able to do much better. And as we go forward, we hope to be able to achieve our design sensitivity of the originally envisioned hardware in the black trace. And even further, we are planning, designing, and already starting to install technologies to enable us in our current facilities to go even farther to hopefully achieve this green dashed line of sensitivity. So over the next few years, we will continue making improvements to the detectors to further improve the quality of the data that we send out to the Open Science Center. And with that, I'm delighted to take questions. I'm sure it looks like there's been a lot of chat, and hopefully our mentors from various sites have been able to answer some questions, but I'm also happy to take further questions.
Excellent. Jenny, thank you so much for that great talk. Okay, yeah, there has been a very